Hello everybody, welcome back to Trigonometry. Today we are in section 1.2 and we're going to be talking about similar triangles. In this section we'll look at the angle sum of a triangle, and we'll also, like I said, talk about similar triangles, and we'll get a few examples in. So first let's talk about the angle sum of a triangle. So you probably already know that the sum of the measures of the angles of any triangle is 180 degrees. And here we've got just any old triangle, not a specific type of triangle. And so you can see we've got three angles here. And now, I don't know if you knew this, you probably already did know this, but if you were to take a triangle like this and just cut any shape of triangle out of a piece of paper and then tear off the three corners, you would be able to align the three angles so that the bottom edge of the three angles makes a straight line or a straight angle. And that's because the interior angles of a triangle always add up to 180 degrees. So here we are at example 1, and this says the measures of two of the angles of a triangle are 37 degrees and 61 degrees. Find the measure of the third angle x. Now I know you could probably solve this one mentally and you don't necessarily need a diagram, but it's a good idea to get into the habit of drawing the triangle for yourself. And so I've drawn us here a little triangle, and I didn't use a protractor or anything to get these angles exactly the right size. We just want to sketch a triangle just to give us a visual aid. And so I've labeled two of the angles 37 degrees and 61 degrees, and I'm going to label the third angle x. And so now what we want to do is write an equation that models what we see in the problem. And we know that the three angles of a triangle add up to 180 degrees, so we can write 37 degrees plus 61 degrees plus x equals 180 degrees. Now, of course, if we subtract 37 from both sides and subtract 61 from both sides, we'll have something that looks like this. And so our angle x is 180 minus 37 minus 61 degrees, so angle x is 82 degrees. And here is example 2, and it's very similar to example 1, only there's a little more algebra involved. It says find the measure of each marked angle. And so we have three angles here, and we have an expression for each angle. And the one thing we know is that the sum of these three angles is 180 degrees. So what we need to do is write an equation where we add these three expressions together and then say that the sum of these three expressions is 180 degrees. And it doesn't matter which one we start with, so I'm just going to start with this one. And so I'm going to write x plus 24, and I've got it in parentheses just because it was in parentheses here. So x plus 24 plus 3x minus 48 plus 1/3 x plus 48, and that's the three angles, and we know that the sum of those three angles has to be 180. Now at this point you can't do anything to the left side as long as you've got these parentheses in place. So we ask ourselves, what good are these parentheses doing? There's nothing that has to be distributed. There are no exponents. There's really no reason for these parentheses to be here except that they're keeping the three expressions separate from each other so that you can see you've got 1, 2, 3 separate angles added together here. So I'm just going to erase the parentheses. They're not really doing anything algebraically. And now we can combine like terms. So I'm going to combine the x terms, but notice that I've kind of got two kinds of x terms if you want to look at it this way. I've got these x terms that have whole number coefficients, and then I've got this x term that has a fractional coefficient. I'm not going to worry about combining those two right now. So let's just write x plus 3x, and that's going to be 4x, and then we'll keep this plus 1/3 x, and then let's combine our three constant terms. So we've got plus 24, minus 48, and plus 48. Now you could just go left to right, but you also could notice that negative 48 and positive 48 are going to add up to 0. So if you add these three numbers together, you're just going to get plus 24. And all of that together equals 180. Now at this point, I would like to eliminate this denominator. I want to get rid of this 3. So we can just remember that we can multiply the left side of an equation by anything we want, as long as we also multiply the right side by that same value. I want to multiply the left side by 3 because distributing this 3 is going to cause that 3 in the denominator to divide out. But because I've multiplied the left side by 3, I'm also going to multiply the right side by 3. And now let's distribute. 3 times 4x is 12x. Then for 3 times 1/3 x, we know that 3 times 1 is going to be 3. In the denominators, we would have a denominator of 1 here if we wrote it down. So that denominator of 1 times this denominator also makes 3. So I've got 3 over 3 times x, and then I've got 3 times 24, which we know is going to be 72. And then on the right side, 180 times 3 is 540. Of course, this 3 divided by 3 reduces to 1. So what I've really got here is 12x plus 1x plus 72 equals 540. And so now, of course, we can combine these two like terms. 12x plus 1x is 13x, and then we've still got our plus 72 and our equals 540. And now to finish up the solving process, we're going to subtract 72 from both sides, and then we'll have 13x equals 468. Divide both sides by 13, and we'll have x equals 36. And of course now we have to take the 36 and plug it into each expression to find the measure of each individual angle. So let's start with the x plus 24. If x is 36, then x plus 24 becomes 36 plus 24, and that adds up to 60 degrees. Okay, now let's do the second expression. So we've got 3x minus 48. If x is 36, that becomes 3 times 36 minus 48, and so that's going to add up to 60 degrees as well. And now we could get the third angle by subtraction. We could say 180 minus this angle minus that angle. But let's go ahead just for the sake of completeness and let's plug our x into this third expression. So it's going to be 1/3 x plus 48. That turns into 1/3 times 36 plus 48. Now 3 happens to go into 36. So 1 times 36 is 36, and then that number divided by 3 is 12. So what we've got here is 12 plus 48, which also adds up to 60. And of course, these three numbers do add up to 180 degrees, so that is kind of a double check for us to be sure that we didn't make a careless error somewhere along the way. Now let's move into similar triangles. So two triangles are considered similar if they have 3 pairs of congruent angles. Triangles that are similar will have the same shape, but not necessarily the same size. So I've got a few pairs of similar triangles here. Let's look at this first pair. You can see that they have 3 pairs of congruent angles. This angle in the small triangle is congruent to this corresponding angle in the big triangle. Both of these angles are right angles. This angle is congruent to that angle. And so the triangles are the same shape, but one is smaller and one is larger. The same thing goes for this pair of triangles. There's a small one and a large one, but because one angle from the small triangle is always congruent to a corresponding angle in the bigger triangle, these two triangles are similar. And notice that they are the same shape. And then you could say the same thing for this third pair of triangles. 3 pairs of congruent angles means that the triangles will be the same shape, therefore they are similar. These two happen to be exactly the same size as well, so they are not only similar, they're actually congruent. These two are not congruent because they're not the same size, but they are the same shape, so they're called similar. So here in example 3, it says triangles ABC and NMP are similar. Find the measures of angles B and C. Now we know that if two triangles are similar, they have 3 sets of congruent angles. And the orders of the letters and the way the triangles are named should help you figure out which pairs of angles are congruent. So the way these triangles are named is telling me that angle A is congruent to angle N, angle B is congruent to angle M, and angle C is congruent to angle P. You can see it here in the diagram as well. So the angle that has one line across the angle is marked as 45 degrees here. Angle A is marked as 45 degrees. And then angle N is also labeled as 45 degrees. So that is just a confirmation for us that those two angles correspond to each other. And then you can see angle C has the double mark across the angle, and so that angle is congruent to the corresponding angle in the smaller triangle that has the double mark across the angle. So since angle P is 104 degrees, we also can know that angle C is 104 degrees. And then if angle M is 31 degrees, that has to correspond with angle B in the other triangle, and so angle B will be 31 degrees. Now if two triangles are similar, not only will they have three pairs of congruent angles, but their sides will be proportional. So if two triangles are similar, then their sides are proportional. Let's take a look at these two triangles. We know these two triangles are similar because angle B is congruent to angle E, angle A is congruent to angle D, and angle C is congruent to angle F. So that right there tells us that these two triangles are similar, and if they're similar, then their sides are proportional. And that means that whatever multiplication or division relationship there is between two corresponding sides, the other pairs of sides have to have that same relationship. So side AB is proportional to side DE, and we can see what the relationship is. It's going to always be either a multiplying or dividing relationship, and you can see that 9 divided by 3 is 3. And so that relationship of dividing by 3 has to hold for the other pairs of sides. So to find side DF, we can just take the 18 and divide by that same 3. 18 divided by 3 is 6. So that tells me that side DF is 6. And the same relationship has to hold for the other pair of sides. The smaller side is just the larger side divided by 3. And so 6 divided by 3 is 2. And so now look, 9 divided by 3 is 3, 18 divided by 3 is 6, and 6 divided by 3 is 2. And that proportional relationship will always hold up in similar triangles. Now there's more than one way to find the missing sides of similar triangles. If the relationship between the sides is obvious, like it was on the last slide where you can just see, oh, obviously I just have to divide by 3, then the length of any missing sides can be found by intuition, and you don't have to write out the proportion. However, sometimes the relationship is not that obvious, and you will need to write out the proportion, which is one ratio equal to another ratio, or one fraction equal to another fraction. So it's great when you can do it by intuition, but I also want you to know how to do it by equation when you can't see the relationship. So let's do example 4 together. It says, given that triangle ABC and triangle DFE are similar, find the lengths of the unknown sides of triangle DFE. Now I think here you probably can do it by intuition, because for the two sides we know, there's an easy relationship between 16 and 8. We can solve this by intuition if we just notice that each side of triangle DFE will have to be half of the corresponding side from triangle ABC, because we see that 8 is half of 16, so this side is going to have to be half of 32. 32 divided by 2 is 16, so that side is 16. And then side DF is going to have to be half of side AB. So half of 24 is 12. And so it's easy to see how that holds up. 16 divided by 2 is 8. 32 divided by 2 is 16. 24 divided by 2 is 12. When you can see it, it's great. But let's pretend for a second that you can't see it, or you're not sure how it's supposed to work. If the relationship between the sides is not obvious to you, then your fallback is to write out a proportion. And the way to do that is to make a fraction using one of the sides you don't know, and then another fraction that's built the same way using two sides that you do know. So what I'm going to do, just to keep us from having to use like double letters here, I'm going to give each side a variable name so that we only have to keep up with one letter at a time. And so one way to set up a proportion is to make a ratio using corresponding sides from each triangle. So this side that is length x corresponds to this side that is length 32. So I could write the fraction x over 32. Now for the other fraction, I want to use the pair of sides that I know, and I want to build the fraction the same way. So if I did smaller side over larger side, then for the other fraction, I also want to write smaller side over larger side. So now I've got x over 32 equals 8 over 16. And I just want to isolate the x. At this point, a lot of students jump to cross multiplying, but you really don't want to do that, because if you cross multiply, the 16 is going to come up here and the 32 is over there. It's okay for the 32 to go over there, but do you really want the 16 to come over here? I don't think you do, because remember, we're trying to isolate the variable. All we need to do is eliminate the divided by 32 part. So all we need to do is multiply both sides by 32. If we do that, then on the left, the 32's divide out. And on the right, we've got 8 times 32 divided by 16. Now you can punch it in your calculator just like that, or if you want to do it mentally, 32 divided by 16 is 2, and that 2 times 8 is 16. So that tells us that the missing side x is 16. Let's do the same thing for side y. So if I want to make a fraction for side y, I'll make a fraction out of the corresponding sides. So I'll put y on top and 24 on the bottom. And that means I need to do the same thing for the two sides that I know. So that will be equal to, again, 8 over 16. And again, to isolate the y, we just need to multiply both sides by 24, and the 24s will divide out from the left side. On the right side, you could use your calculator, and you could say 8 times 24 divided by 16, or mentally you could say that 8 and 16 can both be divided by 8. So let's do that. 8 divided by 8 is 1. 16 divided by 8 is 2. That leaves us with 24 times 1 divided by 2. And 24 divided by 2 is 12. So side y equals 12. Now, just so you know, that's not the only way you can set up those fractions. We were making fractions out of corresponding parts. You can also do it where you make fractions out of two parts of the same triangle. And so let's try that here. We're just going to go through this example one more time, and I want to show you how to set these fractions up a different way. You could say x divided by 8, and if you make a fraction that's x over 8, then what you're going to do is come to the bigger triangle and make another fraction that's built the same way out of the corresponding sides. So our other fraction would be 32 over 16. And now to solve this, we'll multiply both sides by 8. The 8's divide out. So x equals 32 times 8 divided by 16, which we know is 16. And we could do the same thing for side y. So if we write a fraction that's y over 8, then our other fraction will have to be the same two sides from the bigger triangle, and that would be equals 24 over 16. Because side y corresponds to the side that's length 24, and the side of length 8 corresponds to the side of length 16 from the bigger triangle. So now multiply both sides by 8, and we know that y is going to be equal to 12. 24 times 8 divided by 16 will be 12. So I just wanted you to have some different strategies that you could use. So now you can solve these by intuition when that's easy for you to do. If it's not easy for you to do, you have two different ways to set up your proportions. You can make your ratios out of corresponding sides from different triangles, or you can make your ratios out of sides from the same triangle, you just want to build the other ratio the same way with corresponding sides from the other triangle. Whichever way is convenient for you or obvious to you, that's the way you should do it. So here's example 5, and it says find the lengths of sides A and B given that the two triangles are similar. So if the two triangles are similar, then they will have sides that are proportional. So let's look at the side we know from the larger triangle, and that's 25, and we know that's going to correspond with the side that's equal to length 10 from the smaller triangle. And there's not an easy whole number multiplier that will take us from 25 to 10. So we're going to solve this by setting up ratios. And you have a couple of different ways you can do it. I am going to choose to make my ratios out of corresponding sides. And it's always a good idea to set up your ratio so that you have your unknown in the top. That just makes your algebra one step easier. So I'm going to set up one ratio that's A divided by 8. And if I have A over 8, then my other ratio needs to be one where I know both of the sides, and that's going to be 25 over 10. And then to solve this, we'll multiply both sides by 8 to eliminate that denominator. And so then side A equals 25 times 8 divided by 10. And of course 25 and 10 can both be divided by 5. So if we do that, 25 divided by 5 is 5, and in the denominator 10 divided by 5 is 2, and the 8 is still there. And so then we know that 8 divided by 2 is 4, and then 5 times 4 is 20. You can do it like that mentally, or you can just say 25 times 8 divided by 10 on your calculator. And then to set up the other proportion, let's write a fraction that's b over 6. So if I write b over 6, then my other fraction is going to need to be 25 over 10 again. So we'll multiply both sides by 6. And then that gives us b is equal to 5 over 2 times 6, because again, we know that 25 over 10 reduces to 5 over 2. 6 divided by 2 is 3, and then 5 times 3 is 15. So side B is going to be 15. Now, we haven't seen any examples with units yet. We haven't had any like inches, feet, or meters, or anything like that. So let's talk about units a little bit. As long as all the measurements within a single triangle are in the same units, it's okay if the other triangle is measured in different units. For example, one triangle can be measured in inches and the other one measured in meters, and no conversion is necessary. Whatever measurements you have to find, those measurements will be in the same units as the other sides in that triangle. The only time you'd need to do any unit conversion would be if two sides are given in two different units in the same triangle. For example, if one side in the triangle was measured in feet and another side in the same triangle was measured in yards, then you would have to convert feet to yards or yards to feet. But as long as the whole triangle is in the same units, no conversion necessary. So here's example 6. It says workers at the Morganza Spillway Station need to measure the height of the station flagpole. They find that at the instant when the shadow of the station is 18 meters long, the shadow of the flagpole is 99 feet long, the station is 10 meters high, find the height of the flagpole. Okay, here's a diagram for us. So this is obviously the station. They said when the shadow of the station is 18 meters long, so the station is casting a shadow along the ground, and that's 18 meters long. At the same time that they do that, the shadow cast by the flagpole is 99 feet long. And let's go ahead and mark the units. They gave us the measurements in the diagram, but they left off the meters and the feet. So I've put M here for meters and feet here, just so we remember that these two triangles are in different units. Now, why do you suppose that they made a point of saying that the measurements happened at the same instant? It's because we have to know that the sun was in the same position when it made both shadows. And why do we have to know that? Because in order to find this missing side, we have to be able to know that these two triangles are similar. And we'll know they're similar if they have 3 pairs of congruent angles. So we see this right angle here, so that's one pair of congruent angles. Now, because we know that both shadows were created at the same instant, we know that the sun had no time to move when it made both shadows, so that tells us that these two angles right here are congruent. And then because the three angles inside the triangle have to add up to 180, this third pair of angles must also be congruent. And so now, because we know that we have three pairs of congruent angles, we know that the triangles are similar, and that means that the sides are proportional, and we can find the missing height of this flagpole. But we do need to give the height a name, so let's just call it h for height. And we know that since this side was measured in feet, this height, when we find it, will also be measured in feet. All right, now let's go ahead and write our first ratio. And there are, two different ways that you can do this. But what I'm going to do here is I'm just going to write the ratio h over 99. And then that is going to be equal to the same ratio in the other triangle. And that's going to be 10 over 18. So h over 99 equals 10 over 18. Now you see the reason it does not matter that the triangles are measured in different units is that here we have feet over feet, and so the units divide out. And here we have meters over meters, and so the units would divide out here as well. All right, now how do we solve this? We just need to eliminate the 99 in the denominator, so we're going to multiply both sides by 99, and that will divide out from the left side, and that will leave us h equals 10 times 99 divided by 18. And if you want to do this mentally, the 99 and the 18 can both be divided by 9. So when we do that, we have h equals 10 times 11, because 99 divided by 9 is 11, and then divided by 2, because 18 divided by 9 is 2. So all I've done here is simplify. And now we can see that 10 divided by 2 is going to be 5, and so 5 times 11 gives us 55, and that answer is in feet, because it has to be in feet because the other side in this triangle was measured in feet. Now, of course, this is not the only way to set up this proportion, but no matter which way you do it, you will get 55 feet as your answer. And here's example 7. It says, assume that the inner triangle is similar to the outer triangle. Find the length of side C. So this looks like a hypotenuse, but we don't know for sure that this is a right angle. We do know that the larger triangle is similar to the smaller triangle on the inside. And so whenever you have a diagram where two triangles are superimposed on each other like we have here, I like to sketch the triangles separately, at least one of them. So what I'm going to do here is sketch the bigger triangle separately. Now if this is supposed to represent the big triangle, then the bottom side here would be 10 plus 90, so that bottom side is 100. And this long side here would be C. All right, now for the smaller triangle, the bottom side is 90 and the long side is 100. And if it helps, we can get rid of the extra numbers and labels here because we are only concentrating on the small triangle in this diagram now. Okay, so how can we write our first ratio? Well, we could choose to say C over 100. Remember, it's always a good idea to put your unknown value in the top of one of your ratios. So we'll say C over 100, and that means that the other ratio is going to have to be set up as 100 over 90. So we have C over 100 equals 100 over 90, and now we want to isolate the C, so we'll multiply both sides by 100. The 100s will divide out from the left side, and we'll have C equals 100 times 100 over 90. Now, we could do a little simplifying here, but this will not reduce to a whole number. So let's just go to our calculators and enter 100 times 100 divided by 90, and you'll get 111. Remember, in my math lab, they will always tell you how many decimal places to round off to. Here I rounded off to the nearest whole number because none of the given sides have a decimal, so I didn't leave a decimal in my answer. But in my math lab, they will be very specific and they will tell you how many decimal places to keep. And also notice that our diagram did not give us any units, and so I don't have any units on my answer either. But if I did have units in the diagram, I would want to put them on my answer as well. Okay, everybody, that's it for section 1.2. As you know, you'll want to go ahead and do your MyLab homework as soon as possible, definitely before you get into section 1.3. In section 1.3, we're going to shift gears a little bit and really kind of get things in motion. And so I want you to have section 1.1 and 1.2 all squared away before you tackle section 1.3. And I'll see you in the next video. Bye-bye.